Today we are going to talk about the refraction of light. The travel of light through a surface that separates two media is called refraction. So although light waves spread as it moves away from the source, we can approximate its travel as being in a straight line or so-called ray. When a beam of light ray travels through air and encounters on the surface of a piece of glass, as seen in the photo on the left, part of the light is reflected by that surface. The rest of the light travels through the surface is called to be refracted. In the picture on the right, the light is represented by three rays: incident ray, the original light ray, the reflected ray, and the refracted ray. Each ray is oriented with respect to the vertical line called normal. So an angle of incident is called theta 1, the angle of reflection is theta 1 prime, and the angle of refraction is theta 2. The equation that determines the relationship between the media and the angle of refraction is called the Snell's law. The Snell's law basically says n2 times sine theta 2 equals n1 times sine theta 1. So first we look into n. N, or so-called refractive index, is a dimensionless constant that are related to the medium revolved in refraction. If you really want to know how to calculate the value of n equals the light speed, which is the constant c, divided by the velocity of light in that specific medium. So as seen in the three pictures, the relative value of theta 2 depends on the relative value of n1 and n2. When n2 on the second refractive index have greater value than n1, the light ray will be bent toward the normal line, and the angle theta 2 will decrease if n1 is greater than n. This table shows some index of refractions, and notice at the bottom that the indexes are only referring to a specific wavelength of 589 nanometers. So a fact about n is that the index of refraction, n, encountered by light in any medium except vacuum, depends on the wavelength of light. The dependence of n on wavelengths implies that when a light beam consists of rays of several different wavelengths, the ray will be refracted at different angle by the surface. That is, the light will be spread out by the refraction. This spreading of light is called the chromatic dispersion. Generally, the index of refraction of a given medium is greater for shorter wavelengths, correspondingly to, say, blue light, than a longer wavelength, say red light. When a beam of white light that consists of all color in a visible spectrum goes through a different medium, light rays with a different wavelength will be spread out. From the figures above shows how red ray and blue ray were refracted in different ray. Notice that for both cases, blue ray is always bent more than red ray due to its shorter wavelength. Chromatic dispersion explains many common phenomena, like the idea that why the sky is blue and why rainbow have 7 different colors. As the initial angle increases, the angle of refraction gradually increases. As the refracted angle surpasses 90 degrees, there isn't any refracted ray. The light ray is completely reflected, which is called as the total internal reflection. The angle at the moment which refracted angle is 90 degrees is called the critical angle. The critical angle can be calculated using Snell's law, which equals the theta of critical equals arc sine n2 over n1. Here is a practice problem. In figure A, a beam of monochromatic light reflects and refracts at point A on the interface between material 1 with index of refraction n1 equals 1.33 and material 2 with index of refraction n2 equals 1.77. The incident beam makes an angle of 50 degrees with the interface. What is the angle of reflection at point A? What is the angle of refraction there? The solution to this problem is quite simple. By using Snell's law, n2 sine theta 2 equals n1 sine theta 1. We can solve this problem easily. First, we need to find theta 1 related to the normal. Theta 1 can be calculated as 40 degrees. Then we rearrange the equation, and we can easily calculate that theta 2 equals 28.88 degrees.